Hello everyone, my name is Subrata Samanta and I am from IIT Kanpur. So I am your tutor for the physics subject. So in the previous class, we will start the discussing on the charge density instead of a discrete point charge. So we start with a linear charge density and we calculate the total charge for a linear charge density lambda. So if the charges are uniformly distributed, charges are uniformly distributed throughout the region, means that throughout the length, distributed throughout the length, okay, L, then the density lambda becomes uniform. Then the density, the charge density lambda so very specific, the linear charge density lambda becomes uniform. So that means the lambda is not functions of r, okay, is a constant. Okay. So lambda as functions of r equals to lambda, and then the charge q, total charge q is the integral of lambda r dl over line, then the lambda taken out over the integral, so line and dl, and that is the length. So lambda times L, the total length, okay. And yeah, so then the lambda becomes q over L, okay. So remember, in this case the lambda is uniform, the total charge q is uniformly distributed over the length L. So now what is the electric field due to this charge configuration, okay, means that charge density lambda, okay, linear charge density. So to calculate the electric field at any point P, so let us first consider a small element. So let us consider a rod, okay, and the length of the rod L, okay, and let us say the origin at the end of, okay, any end of the rod. So we consider the left end of the rod, we put an axis, okay, and the rod is placed along the x axis I cap and j cap, okay, and the rod is placed along the x axis of length L, right. So to calculate the electric field at any point P in the space, means that in the xy plane. So due to, first we consider a small charge element. So let us consider a small element on the rod. So small charge element, and that is from distance, let us say r, okay. So q d, right, and this one is the dq. No, I think if we consider this one is r, okay. So since that the rod is placed along the x axis, so we consider this one is x, and this the length of this small element is dx, okay. And this one is the origin O, and we calculate the electric field first at point P due to this element, okay. and this distance becomes r. Okay. So the electric field at a point P, due to each charge element, so due to charge element dq is given by Coulomb's law, right. So okay, so is given according to Coulomb's law, d e vector 1 over 4 pi epsilon naught times dq over r square and r cap, right. So this dq can be any of part of this length. Okay, so you consider this portion is dq, the charge of this small element. Okay, so we can consider any at any distance x, okay, this element, okay, and the distance from this element to the point P is r, okay. And then the electric field due to each charge element, okay, becomes this, okay. So r is the distance from the dq to P and r cap is the corresponding unit vector. So this one is r cap, this one is r cap, okay, the corresponding unit vector. Okay, so here r distance from dq to P, okay, and r cap is the unit vector, it's the corresponding unit vector, corresponding unit. So r cap is the corresponding unit vector. So now we use the superposition principles. The total electric field is the vector sum of all these infinitesimal contributions. Okay. So we can choose this small element anywhere in the rod. Okay. So using superposition principle, so using superposition principles, the net electric field is the vector sum of all infinitesimal small element dq. Okay. Using the superposition principle, the net electric field E, net electric field E is the vector sum of all these infinitesimal contributions. Simil dq, right, with a charge dq. So then the E 1 over 4 pi epsilon naught sum over I dqi over ri square then ri cap. Now if we consider, so this infinitesimal element is very small, okay, such that this becomes, the sum becomes converted to an integral, okay, 4 pi epsilon naught integral over dq. Now we can use a continuous variable instead of discrete variables, right. So if we split up this entire rod with a large number of infinitesimal element, okay, dq with a charge dq, okay, then we can use a integral instead of sum, okay, because the sum is converted to an integral. So dq over r square r cap, okay. So this is a continuous variable and this integral over the L, is that the line. Okay. So again this one is a vector integral. Okay, so this is a vector integral. So remember this one is a vector integral. What is mean? That we calculate each component of the electric field separately, okay, in the in each directions of the space, right. So basically we calculate the Ex is 1 over 4 pi epsilon naught dq over r square, okay. And then this is a projecting of, so r cap dot I cap, right. So we projected along the x axis. Now this one is scalar, okay. So this is a scalar, okay, and the integrate over the line. So now it is easy to compute the integral, okay, value, okay. And similarly for the y component, similarly for ey and ez, if there is any z component of. So let us do one example and it becomes more clear. So example 1. So we calculate an electric field on the axis of a rod. So electric field on the axis of a rod, okay. So again we consider a rod. So this one is x axis I cap, the unit vector. This one is y axis, the unit vector is j cap. So we consider a rod placed on the x axis, okay, at a distance. So let us say this one is origin O, and at this point we calculate the electric field. So let us denote this point P, okay. And so basically the point P is the axis of a rod, okay. So the same axis where the rod is placed, and from this point P to the distance of the rod, x naught, okay, and the length of the rod L. So okay, so the question is a non-conducting rod of length L, okay, with a uniform charge density lambda, okay. So for simplicity we first assume a uniform charge density, so again uniform positive charge density, okay, specific positive charge density lambda, okay, and a total charge q, a total charge capital Q, okay, and is lying along the x axis, is lying along the x axis. So this is the statement of the question and the corresponding figure, the right hand side. So if so, in order to calculate the electric field at any point at this point P, so if we specify at the point P, okay, here, so we calculate the electric field at point P, so that is lying on the axis of a rod, okay, at x0 from the left end, okay, so this one is x0 from the left end of the rod, okay. So we first calculate the electric field at point P due to a small element, okay. So let us say consider a small element, the length is dx prime and at a distance x prime, okay. So the amount of charge content in the small segment of length dx prime. So the first let's consider a small segment of length dx prime at a distance x prime from P, and the amount of charge content in this small segment dx prime, the amount of charge content in dx prime is dq lambda times dx prime. Okay. So here we consider lambda is a uniform, okay, and so for the lambda is basically uniform, so q over L, okay, that we discussed in the previous class. So now we calculate the electric field at point P due to this charge element dq. Okay. So due to this charge element dq, and then integrate over the entire length, okay, to get a total electric field. So okay, so we will calculate this in the next class. So first we understand the what is the directions of the electric field at point P. Since that we consider a positive charge, okay, so a positive charge density, so we consider a positive charge density, so then the electric field at P is directed outwards, right? So that means the negative x axis. So this is the directions of the electric field at point P, okay, is the negative x axis, okay. So in the negative x axis, so okay, so in the next class we will calculate the electric field in this charge distributions, okay. Thank you.